Hi everyone, welcome to Data Structures and Algorithms last session, session 7.2, which covers what you call graph interfaces implementations for two use cases. One of them relates to the hop count in a graph. The other one relates to topological search. And this will be the last session on data structures and algorithm. And from next week, we'll start on the uh, machine learning using Python. So at this stage, I am thankful to Jaymeeth Vasava for carrying out this in as part of the study circle in a very uh, what do you call uh, persistent way and doing justice to the topic consistently. Let's look forward to hearing from him. And uh, I can hand over to Jaymeeth Vasava. Go ahead, take it, and let's start reviewing the data structures and algorithms graph session 2. Thanks.
So thank you so much to Prakasha and the EOTF Foundation. So yeah, let's get started with the last session of data structures and algorithm for graphs. So first we'll be implementing the basic header files for the graph, and then we'll be seeing the examples of their implementations. But before starting graphs, let's just quickly recap some of the basics of graphs, of the topic graph. And if you want a detailed explanation on those topics, it is available on the channel and the recordings. So let's get started. So what is graph? It's a flexible data structure typically used to model problems defined in terms of relationships or connections between objects, where objects are the vertices. So 1, 2, 3, 4 are vertices, and the arrows between them or the lines between them are showing the relationship between them. So arrows are the one with the arrows is a directed graph. As you can see, there is a particular direction given to them. The one with just lines are an undirected graph. It means that it's a bidirectional thing. So 1 and 2 and 2 and 1 both are connected to each other. And you can see in the representation as well, the graph the graph G contains VE, V for vertices and a E for edges. So for figure A, which is a directed graph, you can see the set of vertices and the set of pairs for the connections. Similarly, for an undirected graph, you can see the set of vertices and the pairs of the graph. As in figure B, for the edges, the 1 and 2 and 2 and 1 will be considered same in a way. So that is the reason you're not seeing the repetitions in it. Then there is adjacency. So adjacency in directed graph and adjacency in undirected graph. Starting with directed graph, it's a directed edge from vertex A to B. We say that if there's a directed edge from vertex A to vertex B, we say that that A points towards B, but B does not necessarily point towards A. And adjacency in undirected graph, if there's an edge between vertex A and vertex B, it means that A is adjacent to B and B is adjacent to A. Then there is incidence. So in the figure, you can see that for edge 1, 2 is incident from vertex 1 to incident to vertex 2. And in an indirected graph, there is an in degree and out degree. So in degree is the in degree of a vertex is the number of edges incident to it. So 2 has in degree of 2, where first edge is from 1 and the second edge is from 3. Then out degree of 2 is 2, which is for 3 and 4. Then in an undirected graph, as it's in an undirected graph, the degree of the vertex is the number of edges incident on it. Then next is path. So a path is a trail in which neither vertices or nor edges are repeated. So it is essentially a walk with no repeated vertices. Then there is a cycle. So cycle is a path that includes the same vertex 2 or more times. Then connectivity. An undirected graph is connected if every vertex is reachable from each other by following some path. And if it's the same thing true for directed graph, we say that the graph is strongly connected. So let's start with the figure on the right, which is an undirected graph, which has two articulation points, 4 and 5. So articulation points are the points where if we remove them, we lose the connection of the graphs. So you can see that if we remove 4, we lose the connection of 1, 2, 3 with 6, 7, 8. 5, 6, 7, 8. So those are called articulation points. Now, if we come to the image on the right, which is a directed graph, we have a strongly connected component 1 and with the help of 1 and 4, which are connecting 1, 2, 3, and 4, 5, 6. Then there is a concept of adjacency list representation, which is a way to represent graph. Its structure contains a vertex and a list of vertices adjacent to the vertex. Then there are search methods. Search methods are basically how we travel the graph. So there are two important search methods. First is a breadth first search, which explores the graph level by level, visiting all neighbors of a vertex before moving to the next level. Then there is a depth first search, where we try to go as deep as possible along with each branch before backtracking to it. Backtracking happens when we enter a node and we have no other node further to further nodes to discover or travel to. So after that, we start backtracking to it. So after these brief topics of discussion for graphs, let's start discussing the interface for graphs, which are the basic operations and that will include in the header files for the graph. So first is a graph init, which basically initializes the graph with the help of pointer graph. Then in the command also, you can see that there is a match function, which basically determines whether one node is equal to another node or not. So if which does it in form of key 1 and key 2. So if key 1 is equals to key 2, it will return 1, else it will be 0. Next is graph destroy, which deallocates the memory that was allocated by init and frees the memory. And it has a complexity of big O of v plus e, v for number of vertices and e for number of edges. Then graph insert vertex. So it inserts a vertex into the graph specified by the pointer graph, and the new vertex contains a pointer to the data pointer. The complexity of it is big O of v. Then we have a graph insert edge, which inserts an edge to from the vertex, which is specified by data 1 in the command, to the vertex specified by data 2 in the graph specified by the graph pointer. So both vertices must have been inserted previously using the graph insert vertex. So of course, the edge can be formed only when there are two vertices already existing. So for the undirected graph, we will call the graph insert edge twice for the connection of UV, edge UV, first from U to V and second one from V to U. The complexity of it is a big of V. Next is a graph remove edge, which removes the edge from data from pointer, which is from pointer data 1 to pointer data 2 in the graph specified by the pointer graph. And upon return, pointer data 2 points to the data stored in the adjacency list of the vertex specified by pointer data 1. The complexity of it is big of V. Then graph remove vertex. So it removes the vertex matching the data from the graph specified by pointer graph, and all edges incident to and from the vertex must have been removed previously using graph remove edge. So first we have to remove the graph, and then we call the graph remove vertex, and the complexity of it is big O of E plus E. Then graph adjacent list, which retrieves the vertices that are adjacent to the vertex specified by pointer data in pointer graph. The adjacent vertices are returned in the form of an adjacent structure. So a structure containing the vertex matching pointer data and a set of vertices adjacent to it. A pointer to the actual adjacency list in the graph is returned, so it must not be manipulated by the caller. And it also has the complexity of big of E. Then graph is adjacent checks whether whether the point for what the pointer data 2 is pointing at is adjacent to what pointer data 1 is pointing at in the graph, with the complexity of big O of V. Next is adjacency lists with a plural one. So here we have the ADJ list and we have ADJ lists, which is plural one. So the plural one is basically it's a macro which evaluates the list of the adjacency list structures in the which are present in the graph. So each element in the list is of the ADJ list structure that we have defined. And then graph V count and E count are nothing but the count of the number of vertices and number of edges respectively in the graph. With for ADJ lists, V count and E count, all of them having the complexity of big O of one or constant time complexity. So let's start with the a bit of implementation on it before referring to the code. So the adjacency list representation as a listed structures implemented as so the adjacency list structure is implemented as a set, and each structure in the list contains two members, a vertex and a list of vertices adjacent to the vertex. And an individual structure ADJ list will contain those components. The structure graph, that will be a different structure, which will contain the V count, E count, match and destroy from the graph init function and the ADJ lists. So before moving to the program, I wanted to just clarify the way things are gonna work in the program. So with the help of this diagram, so you can see in the first diagram, we are starting to explore, and we are starting with 1. So all the undiscovered nodes are colored as white, and as we are initializing with 1, we will be coloring it as gray, and then we'll be exploring the nodes which are connected to it, which are 2 and 3. We have discovered, and we are done with 1. So as we are done with 1, we will be coloring the node 1 as black, and we'll be starting with 2 and 3. And as 2 and 3 are discovered, we are coloring it as gray, and so on. We'll be doing that for the whole graph. So this is something that we are going to implement or make the interface about in the code. So first, the header file for the graph.h, we will be including these header files. The other ones that are defined by us are list.h and set.h. First, we will be defining the structure of the adjacency list, which will be containing the vertex and the adjacent of a set, which are adjacent to it, to the vertex. Then we will be defining the structure for the graph and having this graph as member. So first we have a v count, e count for vertices and edges. Then match function for matching the vertices, whether one vertex is equal to other or not. Then the destroy function for deallocating the memory. Then then for the colors, you remember that we discussed about the white, gray, black. So white for the undiscovered one, gray for the we are traversing it, and black for we are done with the connections that are done for the node. We'll be coloring it as black. So these are the one that we have already discussed about graph init for initialization, graph destroy for destroying or deallocating the memory, then insert vertex. For inserting the vertex, insert edge, remove vertex for removing the edge, vertex, and remove edge for removing the edge. Then the adjacency list, and graph is adjacent for checking whether it is adjacent or not. And the last, the v count and e count. So now let's get to the program, which is for graph.c. We include the needed header files. And then we start with graph init. So initializing is a simple operation. It's a simple initialization of the graph with these values. And as you can see, we initialize it with the list of adjacency list structures. And then coming to the graph destroy, where destroy destroy basically means that we will be deallocating the memory that was allocated to it. So Just a second, sorry. Okay. So remove first. This is what the block of code does, which removes the adjacency list structure and destroys its adjacency list. Then destroy the list of adjacent list structures, which is now empty. Here, every one of them is removed one by one, and after that, the empty list is destroyed. And this is just a precautionary measure for removing it successfully. Then we have graph insert vertex, which basically inserts a vertex into the graph. So we first check whether the vertex does not already exist in the list that we are working on. So uh, basically checking for the duplicates. If it's not, we insert the vertex, and after successfully inserting the vertex, we upgrade the or update the count of the inserted vertex and with one. Next is graph insert edge. So to insert the edge from vertex which is specified by data 1 to the vertex specified by data 2 here. So we first check for the both the vertices exist in the graph or not, which will this will take care of that. Then we insert the, as you can see, we insert the second vertex into the adjacency list of the first vertex and adjust the edge count here. Next is graph remove vertex. For removing the vertex, first we will check whether it contains the needed vertex or not. Then we remove the vertex. For removal of the vertex, we will be using the list remove next, which is a part of the ADJ list structure. And if we have finally removed the vertex successfully after the needed operations. So here you can see that we are removing it with the help of a list remove next, which is an operation which was done in a linked list one. So after removing this, we will adjust the size of it and the count over here for removing the vertex. Then for a graph remove edge, similar kind of checking is done where the first vertex exists in the graph or not. So basically graph remove edge works by by the vertex that is specified by data 2, this pointer, from the adjacency list of data 1. So after this check, or let's say locate, we remove the second vertex from the adjacency list of the first vertex, as mentioned for here for this and this, and we adjust the count of the edge. Then This graph ADJ list is a structure containing the set of the vertices adjacent to the specified vertex. So this is what it basically does. It locates the adjacency list for the vertex with this, then returns the vertex if it will return -1 if the vertex is not found. It passes back the adjacency list if everything is successful. Then graph is adjacent is basically a check whether the given vertex is adjacent to the other vertex or not. So yeah, so as those were some of the normal interfaces that we'll need for the graph, and how we can do it for some of the practical explanations or examples. So this is the first example, which is for counting network hops. So you can imagine an internet where we are trying to find a best path. So internet is represented as a graph, and we are trying to see the best path, which is the shortest one. So let's say we are starting at node 1 and we are trying to go at node 4. So the possible paths from node 1 to node 4 are node 1, node to node 2, and to node 4. Then node 1 to node 3, then to node 5, and then to node 4. And then one also exists as node 1 to node 3 to node 2 and to node 4. Now the shortest one, which consists of the least hops, are to node 1 to node 2, starting from node 1 to node 2 and ending at node to node 4. So for this implementation, we will be using the breadth first search, and which will be also a function which has 3 arguments. The first is a pointer graph, then the start vertex, and the pointer hops, which contains the list of hop counts that is returned. Then BFS vertex structure will be defined, which will be having 3 members. The data, which a pointer data to the point is a pointer to the data associated with the vertex. Then pointer color maintains the color of the vertex during the search, and the pointer hops maintains the number of hops to the vertex from the start node. So first, we have these needed header files, the graph.h that we just saw in this session, and the list.h. Then we defined the structure for BFS vertex, which has the data pointer, the color, and the hops for containing the hops. And here we defined the function BFS for which has the graph pointing towards the graph, the starting vertex, and the number of hops to track the number of hops for. So first the needed header files, then for the BFS we'll have the these, then we'll initialize all the vertices in the graph first, then for the first vertex, and then the vertices other than the first vertex. Then we initialize the queue with the adjacency list of the start vertex here. Then we'll be starting the breadth first search. So we'll be traversing each of the vertex and the adjacency in the adjacency list. Then we determine the color of the next adjacency list, and then color each white vertex gray and enqueue the adjacency list. So basically the white vertex to gray is basically they have been discovered. White meaning they were not discovered, and we keep on enqueuing it to the queue. Then next is dequeue the current adjacency list with its color, its vertex black. So as we are coloring the vertex gray after them being discovered, after visiting each one separately of the colored vertex gray, once we are done with them, we will be coloring them black. So this is what this block is doing. And as we are done with it, we'll also be destroying it. And after keeping the track of it, we'll pass back the hop count for each of the vertex in the list that we did. And if you can see that the skip the vertices that were not visited in the end with the help of this. So for counting the network hops in the internet, this was the interface and the program. The next example is for topological sorting. So topological sorting is basically the task that how it can be represented and carry out the tasks that are interdependent on each other. One of the examples can also be transactions being done. The example that we're going to discuss over here regarding the classes and the prerequisites that we have for each of the courses in the university. So, let's say, for example, we have university classes. Some are starting classes and some are advanced classes, which needs standalone classes or courses. So to model problems like these, we use a diagram in which vertices represent tasks and edges represent dependencies between them. To show a dependency, we draw an edge from the task that must be completed first to the task that depends on it. So you can see if we only look at the image part of A, so CS100 is a class that can be done alone and it does not have any prerequisites. But if we go to CS200, it needs a prerequisite of CS100, and CS300 needs a prerequisite of CS200 as well as CS100. Similar kind of story is for and 100 and 200 and MA300, but MA300 also needs CS300 as well as MA200. These are the number of cores, by the way, just in case if you are getting confused. Then we have a CS150, which is a standalone course, and it does not have any kind of prerequisites. Now, this is done in a directed graph manner, but if you can see in the image B part of the B part of the image, it is done in a topological sorting manner. So you can see that CS100, as we said, that it does not have any prerequisites, but CS200 does, which is having CS100 as its prerequisite. Same is for CS300, which has a MA100 and CS200 as its prerequisite, whereas MA100 does not have any kind of prerequisite. Same is the story for MA300, which has the prerequisite of MA200. And also CS300 for doing an MA, for taking a class of MA300. So let's discuss topological sorting in terms of programs. So it will be implemented in terms of depth first search. Where you can see the DFS vertex having two members, data and color, and the DFS function containing the graph and ordered. So graph is basically here. Graph is basically pointer to graph, which is the problem represents, and which is the problem that is being represented. And the order is the list of topological sorted vertices that is returned. This. So first, these are the needed header files to start with. Then we have the DFS main with these structures and list element as a member. Then as we are following the same pattern of coloring the gray for traversing or being discovered and stuff. So this is how we'll started with, and then we as this is DFS, we will try to go as deep into the node as possible before going to backtrack. So as you remember, we are going to backtrack only when there are no further nodes to be discovered from the present node and that we reached by traversing. So then we determine the color of the next adjacent vertex and move. The next we move from one vertex deeper than the next vertex, and we discover the one that is white, the vertex that is still colored as white. And after doing it, we color the last, the current vertex after being fully done through the traversing for it. We color it black. So next is the for DFS for the graph, how it will start. So we first initialize all of the vertices that are present in the graph, then perform the depth first search. And ensure that so here, as you can see, the ensure that every component of unconnected graph is searched. So this is basically done because as you remember, I just said that once we start to explore from the one node, or let's say a current node, then we explore as deep as possible before we backtrack. We backtrack when there are no further nodes to discover from the nodes that we traveled. So this is done for each and every node that is present on the graph, so that any of the disconnected or the unconnected nodes can also be can also have its path to be connected with it. So that is the reason why we do it for each and every vertex. So yeah, if we are successfully done if all the operations are done successfully, we'll exit it with the exit passcode of 0. So we are done with the examples, but there are some of the question answers. So the graph implementation present in this presentation, a list of adjacency list structures, but sets are used for the adjacency lists. So first, the linked list is used in place of an array because the list can dynamically expand and contract as we insert and remove the vertices. And secondly, it uses the sets of adjacency list because the vertices they contain are not ordered, and the primary operations associated with the adjacency list, which are inserting, removing, and testing for the membership, basically whether the vertices are a particular vertex is present in the graph already or not, are well suited with the set with adjacency lists. So even if we could have done it with adjacency list, the primary operation which is here is locate the adjacency list of the specific vertices. So a linked list is better suited than to this than a set. Next is question two. Suppose we model an internet using a graph as shown in this, and we determine that the graph contains an articulation point. What are the implications of this? So if if there is an articulation point and that goes down, then as a precautionary measure, you can have it a redundant network which can connect to the another network, to the separating networks, so that there is no permanent disconnection. Because if we lose the articulation point, there is no way we can connect to it or communicate to it. Next is consider a graph that models the structure of airways. Highways in the sky on which airplanes are often required to fly. The structure consists of two types of elements: the navigational facilities called navites for short, and airways that connect navites with which are typically within 100 miles of each other. Airways may be bidirectional or one-way. At certain times, some airways are not available to use. Suppose during one of these times, we would like to determine whether we can still reach a particular destination. How can we determine this, and what is the runtime complexity of solving the problem? So if we perform the breadth first search from a starting point in the airway structure, we can reach any destination if we discover it during the search. So otherwise, the destination must reside in a component of the graph that became unreachable when an airway airway was made unavailable. So the closed airway constitutes a bridge in the graph. So this problem can be solved with big of v plus e complexity or time, where v is for vertices and e is for edges. Next, question 4 is suppose we would like to use a computer to model states in a system. So let's say imagine the various states of a traffic light system at an intersection and the decisions the system has to make. How can we use a graph to model this? So directed graphs are good for modeling state machines such as traffic lights, and in that we can let vertices represent the states and the edges represent the decisions made to get from one state to another. Edges in the graph to get from one state to the next does not imply that the decision can be reversed. So question 5 is when discussing the depth first search, it was mentioned that sometimes it is useful to keep track of discovery and finishing the times for each vertex. So the start time of vertex is a sequence number recorded when the vertex is discovered for the first time and we color it gray. The finishing time of the vertex is sequence number recorded when we are finished with the vertex and color it black. So in the implementation of the DFS presented, these these times were not recorded. So how could we modify the implementation to record the time of travel? So discovery and finishing times recorded during the DFS are important to some of the algorithms. So to record these times, we use a counter that increments itself each time we color a vertex either gray or black. As a vertex is colored gray, we record the current value of the counter as its discovery time. As a vertex is colored black, we record the current value of the counter as its finishing time. So basically, when we start the counter, and as we color it black, we finish it and stop the count for it. So the same thing can be done for the DFS structure that we just discussed in the program and can be added to it. For question 6, the transpose of a directed graph is basically that the directions that are present in the directed graph are reversed. The edges are reversed. So how can we use an adjacency list to represent it? So transpose of a graph is represented by GT. And as we traverse each list, we make sure that vertex V and U both have been inserted into GT by calling the graph insert vertex. Next, we call graph insert edge to insert the edge. Then graph insert vertex runs in big of V time. This operation is called 2E times, where E is the number of edges in the G. Of course, some of these calls will not actually insert the vertex if it was inserted previously. So each call to graph insert edge runs in big of V time. This operation is called once for each edge in the G as well. So thus using this approach, the overall time to transpose the graph is big of VE. Then at the beginning, it was mentioned that many data structures can be represented as graphs. So how might we think of a binary graph as a a binary tree as a graph. So binary tree is a directed acyclic graph. As you remember that it starts with root and then uh, have has two of its nodes, and two of its nodes have two of its children, and so on. So each node has up to two edges incident from it and one edge incident to it. So edges incident from a vertex connect with its children, and the edge incident to a vertex connects to its parents. And the adjacency list of each vertex contains its children in the end. And there is an exception of root node being uh, the one which has up to two edges incident from it, as a root node is the exception as its starting point. So before ending this Q&A, there is also one thing. There are also three things to be mentioned, which are related to this graph topic, which are hypergraph, multigraphs, and adjacency matrix representation. So hypergraphs are similar to the undirected graphs, but which contain hyper edges. Hyper edges connect an arbitrary number of vertices. So most operations and algorithms for graphs can be adopted to work with hypergraphs as well. Then there are multigraphs, which are similar to the undirected graph, but it allows multiple edges between the same two vertices. As with hypergraphs in general, most operations and algorithms for graphs can be adapted to work with multigraphs as well. So third is the adjacency matrix. So it's a way of a graph representation that consists of a V cross V matrix. So um, instead of reading this out, let me show you how adjacency matrix looks like. So adjacency matrix for undirected graph, you can see it acts as a mirror because it is a bidirectional thing. So 1 to 2 is also 2 to 1. So if we have one connected to 0 and one connected to 2, then for the column of 1 into the column of for the column of 0, we'll enter 1 in the ones place as we have the connection of it. Then for the column of 2 space in 1, we will have as we have the connection of it, will represent it as 1. And if we do not have a connection, it will be represented as 0. So it's a binary thing, 1 for the connection and 0 for no connection. So uh, as also mentioned that because it's a bidirectional connection, the matrix that will be formed for the undirected graph will be a mirror image diagonally from the matrix. For the adjacency matrix in the directed graph, you can see the arrows being incident from and on. So starting with 0, 0 has not been incident, and there are no edges that are being incident on 0, but 0 is being incident from uh, on 1 and 2. So for zeros rows, we will enter 1 for 1 and 2 for 1 and 1 for 2. Then as 1 is not does not incident it, 1 is being incident on one is being incident from 0, 2 and 3. So those will be the values for 1 from the 2 and 3, and same as for 3. 3 is not being incidented on any from anyone, so it's 0 from all the way, same as 0. So yeah, this is was the whole presentation regarding the graph and its implementation. So yeah, thanks a lot for listening, and I hope it helped.
Thank you, Jaymeeth. Excellent presentation and Q&A, and with the code and examples for the graph. This will be very useful for the edge uh, projects, especially edge computing. And I hope this can be reused, as well as you can work in Python on this translation, or it could be rewritten as a separate code. So let's move on. With this, we'll close the data structures and algorithm sessions. Those who want to go through the entire series can go through the sessions 1 to 7 with certain sections and partitions so that we can absorb it. And the next we'll be starting on the machine learning using Python. Coming week, details will be made available once Jaymeeth has reviewed what exactly needs to be done in the ongoing classes from next week, and that will last probably 3 weeks. So by end of May or June beginning, we'll be able to wind up this uh, study circle for the PG diploma in AI, as well as AIML circle, what we call it. Thank you, Jaymeeth, and excellent. Have a good weekend, and let's just gather back on again on the coming week. Thank you.